Hey everybody, can you hear me okay? Let's see. Just put yes in the chat box if you can hear me. I think you can. Okay, perfect. All right, so today we are covering some we're doing roots. Roots is a part of the exponent chapter, so it's kind of the rules. I mean, one is almost the opposite of the other. These are great questions. There's a lot of rules to memorize and to then be able to apply. So as long as you feel good about the rules, there's certain things that you'll be able to do very quickly and efficiently when it comes to solving roots. And this is the same thing with exponents. So what I want to do here is I want to give some problems that are based on some of these rules and kind of talk about some of the traps that can exist when dealing with this question type. So I'm going to put a question up here. I'm not going to tell you what the rule being thrown at you is, but why don't you get your answer, put it in the chat box, and then we'll go from there. All right, so start with this one first. All right, so is anyone aware of what the trap is in this question? Like, what are they trying to get you to do here? Because there is a trap. Because this problem looks pretty appetizing. Not quite, but that could be considered a trap. What I'm getting at is the fact that this particular problem, they're trying to get you to take the square root of both sides of both values first, which you can't do according to this rule. The rule stipulates that you have to first combine and then take the square root. So if you're ever wondering about that, a very simple example we give, and we give this in the chapter, square root of 16 plus square root of 9 is square root of 25, right? which ends up being 5. Now, square root of 16 plus square root of 9 is 4 plus 3, which is 7. Clearly, these two things aren't equal to each other. So that's the way to kind of look at this here. Something to keep in mind as you're doing these questions, because then all you have to do here is, of course, apply this rule, and now you're just adding within the root, right? So you're getting common denominators. So what you've got here is common denominator of 100, so 4x squared over 100 plus x squared over 100, and then 5x squared over 100, and then from here, you can kind of take the square root of each piece of that's under the root. Square root of x becomes the absolute value of x. Square root of 5 is just, of course, the square root of 5. Square root of 100 is just 10, and there's your answer there. So it's x root 5 over 10. Yeah, I mean, there's different types of traps. I just wanted you guys to be aware of what the trap is that's based on the rule here. So again, that's just one rule. We're going to do a few more now just to get you guys acclimated with this. And like I said, a lot of the stuff in roots is very similar to things that you're doing in exponents just from your mindset perspective. Now, there's multiplication and division of roots. That's the next thing I want to kind of talk about here. Then I want to do a little bit of approximation with roots. But we'll start with division, and then we'll go from there. So take a look at this. All right, great. So it looks like most of you guys knew what to do here. So there's different things going on with x. Remember, we're trying to get x over y. So with x, 14 goes into 28 twice. So that's not bad. We have 2 root 200. Now, you can reduce the 200 out if you want to, like simplify that given root, or you can, of course, wait. It's totally up to you. Then you can move on to the y. So we leave the 36 alone. We have root 80 over root 10. Now, 10 goes into 88 times, so y actually becomes 36 root 8, okay? Then we can bring these together. So the x is 2 root 200. The y is 36 root 8. 2 reduces that down to 18, sorry. And then look, 8 goes into 200 25 times, and then the square root of 25 is just 5. Now you can write this out, you can do it in your head, but ultimately that equates out to 5 over 18. Like I said, there's different ways you could have dealt with this, right? This is just, you know, a nice method that allows us to kind of get rid of the root one fell swoop without having to simplify it out, which is really nice. So the answer here is 5 over 18. Now, another thing I want to talk about is the approximation of roots. There's some we tell you to memorize, but then there's also just approximation in general. And the good news is there's a very easy process to deal with that. I'm going to jump right into approximation of roots that are not square roots. But the process that you'll follow for all of them is really the exact same. So I'll give you guys a couple minutes. This is something that once you get it down, it's pretty simple. But let's start with this, and then we can kind of go from there. All right, I see a lot of good answers here. Do you guys feel like you have a good process for estimating roots? I mean, based on your okay. Well, there's one no. I was going to say based on your answers, I feel like you do, but if you do not, I obviously want to talk about this. All right, well, for those of you that put the correct answer, my guess is you do have some sort of process here that you like. Now, The process is pretty simple. Like I said, this is the same thing for square roots and cubed roots and fourth roots and fifth roots. You're just finding the perfect root above and below. So for example, root 9 actually, there's no for example. Root 9 is just 3. So that's not bad. But when you take the cubed root of 9, you're looking for what's below it and above it, the perfect cubed roots. The one below is root 8, and then what's above it? Well, that's going to be the cubed root of 27. If we're trying to make this to scale, it's a little bit further off. This is 2, this is 3. Clearly 9 is closer to 8, so we could say it's about 2.1, right? Now, that's the process. It is that simple. The square root, this fourth root of 9, let's do that one. Well, what's the closest fourth root? It's actually going to be the fourth root of 1. Remember, 1 is a perfect cube, perfect square, perfect fifth, everything. And then above it is going to be fourth root of 16. So we're going to have a 1 here, a 2 here. 9's like roughly in the middle. Remember, you don't have to be perfect on this. So we're talking 1.5. So it's 3 plus 2.1 plus 1.5. When we do that, we see that that becomes 3 plus 2.1 is 5.1, and then plus 1.5 is roughly 6.6. So it's between 6 and 7. So hopefully that process resonates with everybody. It seems like it's something that's pretty doable. I agree that it is. So it's just something that you want to, try to work on when it comes to estimating roots, square roots, fifth roots. And you can mess around with it. Like once you do it a couple times, I think you'll see it's nothing that crazy. All right. So we talked about addition, subtraction with radicals. We did some division with radicals. I want to talk a little bit about rationalization of radicals when they're in the denominator of an expression. GMAT loves to test on this stuff too. So let me pull up the first question. As always, I'll give you guys a few minutes and then we'll chat. All right, so this is all about rationalizing the denominator, right? What we're talking about here is how to get rid of the root. So we have 3 plus root 5 over root 5. We're going to multiply by root 5 over root 5, right, to get rid of the roots here. Now, when we do that, the denominator is pretty simple. That's going to be just a 5. And when we distribute the root 5, that's going to be 3 root 5 plus 5. And from here, we're going to then try to, actually, no, we don't actually have to factor out here. So in fact, that's all we need to do here. Wait, no, hold on a second. I wrote this backwards. Give me 1 second to rewrite this. But the point is, anytime you're in this situation where you have a root in the denominator, first and foremost, what they're testing is the idea that you're going to need to get rid of or rationalize that root in the denominator. So what the GMAT cares about is the fact that you can't have a root in the denominator of of a fraction. And sometimes they do this with multiple values in the denominator and sometimes with singular ones. So again, the way to deal with this is multiply by root 5 over root 5. So we're going to have 3 root 5 plus regular 5 over 5 on the bottom here. So the last step actually is not factoring out. You can distribute and distribute. That's going to give you 3 root 5 over 5 plus 5 over 5. That's going to be 3 root 5 over 5 plus 1. And that's going to give us a value of C. All right, now I want to do one where we're talking about the conjugate. So take a look at this here. All right, take a look at this guy here. All right. Yeah, well, this question here, I would say this is medium to hard, this particular question. All right, so what do we have to do? We have to rationalize the denominator, root A minus A. So we're going to do root A plus A over root A plus A here. That's how we're going to rationalize it. Now remember, when rationalizing, what's happening is we have the difference of squares in the denominator, which makes life pretty easy. So you're just going to do root A squared, which is A minus A squared. And then in the numerator, you have A root A, and then you have plus A squared. You can actually factor out an A, and that's going to be root A plus A. You can factor out an A here, 1 minus A, and then all of a sudden, oops, that goes there. The A's cancel. Let me move this down. The A's cancel, and you're left with A squared, root A squared plus A over 1 minus A. And that's it. And that's answer choice A. So does anyone have any questions about that? All right, so if we have no questions here, then we can jump into other questions. You guys have questions in general? Oh, question about the previous example? Yeah, what's your question? The numerator doesn't disappear because we distributed it to both terms in the numerator. Oh, the numerator root? Because we had to multiply, it does. It disappears here, but then we also multiplied 3 by root 5, so you had to keep the root 5 there as well. All right, cool. Does anyone have any other questions? Is it advisable to form an equation along with reading the problem? It depends. I mean, if you feel like it's going to throw you off, then don't. If you feel like you're in a position where you can read the equation, or you can read the question and formulate the equation simultaneously, then yeah, I think it's something worth doing. But this is stuff you got to kind of practice with to know what works best for you. Avoid careless math mistakes. I mean, I think eventually practicing under time and conditions, and then also recognizing what the careless mistakes are, when you make them, why you make them, etc., I think is always going to be helpful. You know, because they come in a variety of shapes and sizes, and there may be different reasons why you're making those mistakes at different points in a test. You know what I mean? So you really got to just be very careful in doing that analysis to see what exactly is going wrong and why. Any other questions? Put a short question. Sure. What's the question? In the meantime, does anyone else have any questions? Other questions? All right, well, if there are no other questions, I think we can call it. I think this is good. So we'll be back on, how many odd numbers? Oh, no, we're not going to do a new question here. We're we're done for our questions. That question is probably actually on the forums too, where you can get an answer. So yeah, if there's nothing else here, then we can call it. This was good though. I think we'll obviously get into a new topic next week. Keep us updated. If you need anything, reach out to us. We are here. We're happy to help. Have a safe, healthy weekend. Study hard, and I'll talk to everybody soon.